So in the previous lecture, we discussed a one-dimension heat equation, problem 1. So what is the difference between problem 1 and problem 2? So problem 1 is based on a heat conduction in a bar whose both ends are having a fixed temperature. That means homogeneous boundary. Now a problem 2 is based on the heat flow in a bar with insulated ends. Insulated ends, that means no heat flow through both ends. So basically in this problem we consider both ends of the rod are insulated. No heat flow through both ends. Instead of having a fixed temperature at the two ends of the rod. That means homogeneous boundary condition. Therefore, the boundary condition of problem 2 is the derivative of u with respect to x at x is equal to 0 is equal to 0. That means no heat loss from x is equal to 0 left ends. And the another boundary condition del u by del x at x is equal to L is again 0. That means no heat loss from x is equal to L. That means right ends. So thus, the initial boundary value problem is given as one-dimension heat equation. We solve this one-dimension heat equation whose both ends are insulated. Therefore, the boundary condition are ux0t is equal to 0, uxlt is equal to 0, and the initial condition we consider ux0 initial condition, that means the time t equal to 0, ux0 we consider fx, and this is called initial distribution of temperature. Now uxt is nothing but a temperature which is depends on the space x and time t. Now we solve a problem 2. So first we solve the equation 1 using a separation of variable method, which will be discussed in a earlier lecture, in a previous lecture. So again I repeat some concept. Let us consider the solution form. uxt is equal to capital X of x, t of t. Now differentiate equation 5 with respect to x 2 times and with respect to t 1 time. So we get del square u by del x square is equal to x double dash t, and del u by del t is equal to x t dash, where x double dash is a d square x by dx square, t dash is a dt by dt. We input both value del square u by del x square and del u by del t in equation 1. Therefore, we get the PDE form is xt dash is equal to c square x double dash t. Now we apply a separable variable method. So obviously we convert this form in this form, x double dash upon x and t dash upon c square t. From equation 6, the given PD become a OD whose left hand side and right hand side both are equal. The left hand side depends only on x, right hand side depends only on t, and therefore we consider this equation is equal to constant k. So we get 2OD like this first term is equal to k and the second term is also equal to k. Now this is the second order OD. So we consider the different case, k greater than 0, k less than 0, and k equal to 0. And each case, we find the solution of the given initial boundary value problem. So now first we consider k greater than 0. So k equal to p square, p not equal to 0, then the 2OD obtained as x double dash minus p square x is equal to 0 and t dash minus c square p square t is equal to 0. The auxiliary equation of this form is m square minus p square is equal to 0. So m is equal to plus or minus p. And plus or minus p, so this is the real and different root. So we write c1 e raised to px plus c2 e raised to minus px. Similarly, here t dash is equal to c square p square t. So m is equal to c square p square, auxiliary equation of this form. Therefore, we write the solution form is t of t is equal to c3 e raised to c square p square t. Now combine both, then we get uxt is equal to c1 e raised to px plus c2 e raised to minus px, c3 e raised to c square p square t, where c1, c2, c3 are arbitrary constant. Now applying the boundary condition, equation number 2. So first we differentiate equation 8. First we differentiate equation 8 with respect to x. So del u by del x is equal to p c1 e raised to px minus p c2 e raised to minus px. This term is as it is. And then we apply the first boundary condition, equation 2, which is given as when ux is equal to 0. That means del u by del x is equal to 0 when x is equal to 0. So we input this value in equation 9, we get this term is 0. So 0 is equal to pc1 minus pc2, because e raised to 0 is 1, into this term. So implies 0 is equal to p common c1 minus c2, and this term is nothing but t of t, the solution of t of t. So we write t of the function of t. So implies 0 is equal to c1 minus c2, because p not equal to 0 and the solution from t of t also not equal to 0. So we get c1 is equal to c2. So we apply the first boundary condition for the k greater than 0 case. We get c1 is equal to c2. Now we input this c1 is equal to c2 in equation 8. Then equation 8 becomes uxt is equal to c1 is equal to c2, so c1 is common. Therefore c1 e raised to px plus e raised to minus px into c3 e raised to c square p square t, which is called equation number 10. Now we are applying the again boundary condition equation number 3, and this is based on the again the partial derivative. So differentiate equation 10 with respect to x for applying the boundary condition equation 3. So del u by del x is equal to p c1 e raised to px minus p c1 e raised to minus px into c3 e raised to c square p square t, equation 11. So again applying the boundary condition equation 3 when the equation is ux is equal to 0. The boundary condition is ux is equal to 0 when x is equal to L. So we input both value in equation 11. So this term is equal to 0. So 0 PC1 x is replaced with L e raised to PL minus e raised to minus PL. In this term C3 e raised to C square P square D. So implies 0 is equal to PC1 e raised to PL minus e raised to minus PL. This form is the T of T. Now T of T, we can't consider 0. This term is never 0 because P not equal to 0, length not equal to 0. So exponential function, this e raised to PL minus e raised to minus PL is not equal to 0. C1 we can't consider 0 because if we consider C1 is 0, C1 is 0, we know that C1 is equal to C2, so therefore C2 is 0, and C1 and C2 both are 0, then the solution x of x is 0, and which leaves the trivial solution. So therefore, all term which is not equal to 0, but equation is right hand side is 0. Therefore, we can say the non-trivial solution of equation 1. Equation 1, that means one dimension heat equation. So non-trivial solution of equation 1 does not exist which are satisfied the given boundary condition. So again, for k greater than 0 case, the non-trivial solution of equation 1 does not exist which are satisfying the given boundary condition. Now we discuss case 2, k less than 0. The procedure is similar, only the change here k less than 0, so k is equal to, we consider minus p square. Then the given 2 OD obtain as x double dash plus p square x is equal to 0 because we replace k is equal to minus p square in a previous 2 OD's equation. So we get x double dash plus p square x is 0 and t dash plus c square p square t is equal to 0. So the auxiliary equation is m square plus p square is 0. Therefore we write m is equal to plus or minus pi. Plus or minus pi, so complex root, and complex root, so we write x of x is equal to c1 cos px plus c2 sin px, because here the real part is 0, only the imaginary part is p. So c1 cos px plus c2 sin px. And in this equation, the similar procedure, but this is the first order OD, so we get m is equal to minus c square p square. And then we write the solution T of t is equal to c3 e raised to minus c square p square t. So therefore the general solution for k less than 0 case, x of x into t of t is nothing but uxt is equal to c1 cos px plus c2 sin px into c3 e raised to minus c square p square t, which is called equation 12. Now, for this case, k less than 0, we get uxt is this. We are applying the boundary condition equation 2 and equation 3. So obviously, first we apply equation 2. So we differentiate 12 with respect to x. So del u by del x is minus pc1 sin px, pc2 cos px into c3 e raised to minus c square p square t. We are applying the boundary condition equation 2. Ux is 0 when x is 0. So 0 is equal to pc2 cos 0 is 1, sin 0 is 0. So therefore pc2 C3 e raised to minus c square p square t. Sorry, here e raised to minus c square p square t. So implies 0 is equal to pc2 into t of t, and implies 0 is equal to pc2, and implies c2 is equal to 0 because t of t not equal to 0 and p not equal to 0. Hence equation 12 become uxt is equal to c1 cos px into c3 e raised to minus c square p square t, because in this 12 number of equation 12 we input c2 is equal to 0, then we get this. Again we apply the boundary condition equation 3. We differentiate equation 14 with respect to x. So therefore del u by del x minus pc1 sin px c3 e raised to minus c square p square, which is called equation 15. Now in 15 we apply the boundary condition ux is equal to 0 when x is equal to l. So we write 0 is equal to minus pc1 sin pl c3 e raised to minus c square p square t. So implies this term is t of t, so minus pc1 sin pl. So obviously t of t not equal to 0. C1 also we can't consider equal to 0. So obviously C1 not equal to 0, because C1 is 0, then implies x of x is 0. So C1 is not equal to 0. T not equal to 0. Therefore we consider sin PL is equal to 0. Sin PL is 0 implies PL is equal to n pi. So P is equal to n pi by L, where n is 1, 2, 3 up to n. So hence, the solution of equation 1 satisfying the boundary condition. Therefore, the input P is equal to n pi by L in equation number 14. We get equation number 14, we input x, P is equal to n pi by L. So we get uxt is equal to C1 cos n pi by L into x C3 e raised to minus c square n square pi square by L square into t. Now C1 and C3 constant we consider Bn. So Bn cos n pi by L into x e raised to minus c square n square pi square by L square into t. Now in this equation, we are applying the superposition principle. The solution of equation 1 satisfying the boundary condition is given by uxt is summation n is 1 to infinity bn, sorry, an, yeah, bn. We consider an is also constant, bn is also constant, but here term is cos, so we consider an. So an cos n pi by L into x e raised to minus c square n square pi square by L square into t. So again, I repeat, for k less than 0 case, the solution form is equation number 16, which satisfied both boundary conditions. Now we consider case 3, k equal to 0. So let k equal to 0, then the 2 OD obtained as x double dash is 0, t dash is 0. So m is 0 2 times, m is 0 1 time. So m is 0 2 times, so the solution is c1 plus c2x, and m is 0, so the solution t of t is constant. So the general solution of the form when k equal to 0, we write uxt is equal to c1 plus c2x into c3. Now first differentiate equation 17 with respect to x for applying the boundary condition equation 2. So similar procedure for k less than 0 and k greater than 0. We apply the boundary condition first equation 2. So first we differentiate. So del u by del x is a C2 into C3. So in this equation, ux is 0. We are applying the boundary condition when x is 0. So 0 is equal to C2 into C3 implies C2, 0 is equal to C2 and T of T is a C3. So T of T not equal to 0, then we get T2 is 0. Hence, the equation 17 become, that means here C2 is 0, so uxt is equal to C1 into C3. Now we are applying the boundary condition equation 3, differentiate, then we get 0. So this is the equation number 20. Again, the apply boundary condition equation 3, ux is 0 when x is L in equation 19. Sorry, in equation 20, we get the solution of equation 1 we satisfied the boundary condition. Because here we get uxt is equal to C1 into C3. And we consider C1 into C3 is equal to A0 by 2 constant. Because this is the constant form. And constant form whose derivative is 0. So this is satisfied the boundary condition. So thus, the solution of equation 1 satisfy the boundary condition equation 2 and equation 3 which is given as uxt is equal to A0 by 2 plus summation n is 1 to infinitive an cos n pi x by L e raised to minus c square n square pi square by L square into t. So equation number 22 is the solution of a given equation 1 which satisfied both boundary condition. So for k equal to 0 and k less than 0, we get the solution form which is satisfied the boundary condition. Now we apply the initial condition equation number 4 where u is equal to fx when t equal to 0 in equation 12. So in equation 22, so we get fx is equal to, because ux0 is equal to fx. So fx is equal to a0 by 2 summation n is 1 to infinity an cos n pi x by L. Because e raised to 0 is 1. So we get equation number 23. This is the half range cosine series. We get half range cosine series expansion of f of x in the interval 0 to L. Therefore, the Fourier series coefficient a0 and an is defined as a0 is a 2 by L 0 to L fx dx and an is a 2 by L 0 to L fx into cos n pi x by L dx. Where n is 1, 2, 3 up to n, so on. So, a problem 2, heat flow in a insulated ends. That means no heat flow in both ends. So we find the solution of this heat conduction in a bar whose both ends are insulated ends, which is the solution form is equation number 22 where a0 and an is the Fourier half-range cosine series. Now we take the one example. Example is find the temperature in a thin metal rod of length pi with both the ends are insulated and the initial temperature of the rod is Kx. So again I repeat the question. Question is find the temperature in a thin metal rod of length pi. So here given that the length L is pi. Also given that both ends are insulated. So obviously we use a problem 2 because the problem 2 is based on the insulated ends. Third one, here given that the initial temperature of the rod is Kx. So thus we define the initial boundary value problem of this given problem. The mathematical form is one dimension heat equation, equation 1. Equation 2 and 3 both are boundary condition, and third equation 4 which is called initial condition. In this problem where we consider L is equal to pi, an initial distribution temperature Fx is given Kx. So therefore the given problem is similar to the problem 2 except the difference that length L is pi and the initial distribution temperature Fx is Kx. Therefore, the solution form of the given problem is given by uxt is equal to a0 by 2 plus summation n is 1 to infinity an cos n pi x by L e raised to minus c square n square pi square by L square into t, where a0 is a 2 by L 0 to L fx dx and an 2 by L 0 to L fx into cos n pi x by L dx. So now we find the coefficient a0 and an. So L is a pi, so 2 by pi 0 to pi, the function fx is a kx, so kx dx. Now we integrate them and we input the integration limit is 0 to pi, so 2k by pi x square by 2 0 to pi, so pi square by 2 2 cancel, pi cancel, so we get k pi. So a0 is k pi. Similarly we find an. So L is replaced with pi, so 2 by pi 0 to pi, fx is the initial distribution temperature is kx, so kx cos n pi x by L. L is pi, so pi cancel. So this is equal to 2k by pi x cos nx dx. We use integration by part. We consider x is u and cos nx is v. So the integration form is this. X cos nx integration is a sin nx by n minus the derivative of x is 1. Again the integration of this box is sin nx is minus cos nx upon n square. Limit is 0 to pi. So we get 2k upon pi minus 1 raised to n upon n square because cos n pi minus 1 upon n square. So this is the solution of an. Now we input A0 AN and length L is equal to pi in equation number 5. So we get UXT is equal to K pi A0 by 2. So K pi by 2 plus summation n is 1 to infinity AN, that means this value, into cos n pi x by L. So pi pi cancel. So cos nx e raised to minus c square n square pi square by L square. So L is again pi square cancel into t. So this is the solution of the given problem whose both ends are insulated. Length of the rod is L is equal to pi and initial distribution temperature is Kx. Thank you very much. Now in the next lecture we discuss a one dimension wave equation, and also we discuss a different problem which is arrived in a one dimension heat equation. Thank you.